So in this video, we are going to cover amines to a certain extent and ammonium salts. Amines are basically derivatives of ammonia. And they are pretty important functional groups in organic chemistry. So they don't typically, well, they don't undergo substitution and elimination reactions like alcohols and alkyl halides and stuff like that. However, they can be used and are actually our most common organic bases. They're weak bases. Some of them can be strong, but usually they're weak bases, and they are awesome nucleophiles. So we're going to do a lot of the reactions with amines in upcoming chapters with carbonyl compounds. There are a couple of reactions I want to show you in this video, especially as they react with acids and the synthesis of an aromatic, or in other words, an arylamine, and also some chemistry, some interesting chemistry that we can do with ammonium salts. So these things are categorized just like we categorize carbons and alcohols, but they're categorized just a little bit differently. They're categorized by the number of alkyl groups that are on the nitrogen. So the number of alkyl groups that are bonded to the nitrogen. So unlike alcohols, right, where we're categorizing the alcohol based on the carbon that it's attached to, we're going to actually categorize an amine based on how many alkyl groups are on the nitrogen. So for example, a primary amine will have one alkyl group on the nitrogen, and then the nitrogen will have two hydrogens bonded to it and a lone pair of electrons. So that's a primary amine. A secondary amine will have two R groups bonded directly to the nitrogen, and then a hydrogen and a lone pair. A tertiary amine, you probably guess, will have three R groups directly bonded to the nitrogen, and then the lone pair. And then a quaternary ammonium salt. So our ammonium compound. So the ammonium ion, NH4 plus, right? We can create ammonium compounds. Don't have to have just hydrogens attached to the nitrogen. We can have four things, hydrogens or R groups, bonded to the nitrogen. The nitrogen will have a positive charge, and then there will be some anion that's coordinated with it, right? So ionically bonded to it. So with these little ionic compounds, these are when those R groups on the ammonium salt are hydrogens, or even if just one of them is a hydrogen, you can think of that as an acidic compound, like a weakly acidic compound, right? So that's sort of like a little delivery system for a hydrogen, or a proton, I should say. And the intermolecular forces of attraction for these different categories of amines are going to differ a little bit, right? Because if you notice that in the primary and the secondary amines, there are hydrogens directly bonded to the nitrogen, and the nitrogen has a lone pair of electrons. So right away, we know that those primary and secondary amines can hydrogen bond with themselves. So that's going to affect their physical properties. Notice in the tertiary amine, however, that even though there's a lone pair of electrons on the nitrogen, it is not directly bonded to a hydrogen. And so tertiary amines cannot hydrogen bond with themselves. This is like when we were talking about alcohols versus ethers, where the alcohol had an oxygen directly bonded to a hydrogen. So alcohols can hydrogen bond with themselves, but ethers can't, right? Kind of reminds me a little bit of that. All of these can be used as bases. What I'd like to do first, before I dive into the physical properties, is get the nomenclature out of the way. There are multiple different ways that we can name amines. I'm going to try to stick to just common and systematic. And I want to break this into a couple of categories. So we're going to have common, and I'm going to call it systematic instead of IUPAC. Because there's a couple of systematic methods, and I'm going to stick to just one of them. The other thing I want to do is when I break this into not just those two categories, but also categories of amines. So like we've categorized them according to the number of alkyl groups on the nitrogen, but also we have aliphatic amines and aromatic amines. And under those two umbrellas, we actually have a couple of different categories. So let me start out with the aliphatic. So in aliphatic amines, we have a nitrogen bonded to alkyl groups, right? In the other category, we'll talk about aromatic amines, and that is going to be a nitrogen that is bonded to an aromatic group. And in these two categories, we can also stuff in heterocyclic amines, meaning you have a ring, and in the ring, one of the positions is taken up by a nitrogen. So let's just start with common nomenclature. In common nomenclature, we're going to name the alkyl groups bonded to the nitrogen, and then we're just going to follow it up with the word amine. So name the alkyl groups on the nitrogen in alphabetical order, followed by the word amine. So while systematic nomenclature makes it really easy to draw a structure from a name, common nomenclature is really kind of, well, it exists for a reason, right? We commonly call these particular molecules by their common names. So common nomenclature doesn't mean it's not important or as important as systematic. Systematic is just an easy way to quickly identify exactly what the structure looks like because there are numbers and like it's really easy to figure out where everything is. With common nomenclature, it's sort of like if you're hanging around the lab, what do you call this molecule, right? Nobody's listing off the 2 dash blah 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 dash 8 dash. No one's talking like that. So you could take a methyl group. You name a primary amine here as methyl because this is the alkyl group that's on the nitrogen. And follow it up with the word amine. All one word. Methylamine. That's it. We could have, for example, We saw this group before. We have an aromatic ring bonded to a methylene, which is then bonded to an amino group. That is what that thing is called, by the way. It's an amino group. So these are just derivatives of ammonia, right? NH3. That group, though, that phenyl ring or that benzene ring bonded to a methylene, that's a benzyl group. So this is benzylamine. How about if we have two R groups on the nitrogen, instead of just drawing primary amines, we could draw a secondary amine. So now we have two different alkyl groups that are bonded to the nitrogen. We're going to list them in alphabetical order and follow it up with the word amine. We have an ethyl group on the right and an isopropyl group on the left. So, well, might as well do a tertiary amine while we're here. So I could have three methyl groups. It's worth noting that I'm not drawing in the lone pairs on the nitrogen, but they are there, right? So even the tertiary amine has a lone pair, meaning all of these nitrogens are sp3 hybridized, right? We got four bonding, or we have four electron domains, I should say. So this is trimethyl amine. So that's our common nomenclature. But you could see that it might get a little convoluted using common nomenclature if there were substituents hanging out on any of those alkyl groups, right? That's where systematic nomenclature comes in pretty handy. So one particular type of systematic nomenclature is going to be where you replace the suffix E from the alkane. So you find your longest continuous chain, and you're going to replace the E from the alkane name and that'll be your parent. And you're going to replace it with the word amine. So in that way, you're essentially naming these amines as alkanamines. That's sort of like how we would end up pronouncing it. Let me show you an example. So another primary amine. Hopefully you can hear me okay. We have a massive thunderstorm happening. We've got, let's see, 1, 2, 3, 4 carbons in the longest continuous chain, right? So that would have been butane, but we're going to drop the E and we're going to put amine. So this is butanamine. If we have a substituent hanging out, so like we have a chloro group there, it'd be tough to use common nomenclature and let you know exactly where the chloro group is, right? But our longest continuous chain of carbons that bears the functional group, so that means the one that the nitrogen is attached to, right, is going to be the lowest numbered carbon, giving priority to our functional group. we have 3 carbons in our longest continuous chain, and the chloro group is actually on the second carbon. So I can number these just to show you what I mean. And so this is 2-chloro. That would have been propane, but it's propanamine. Right? Because we're going to drop the E from the propane and just put the word amine. If we have a secondary or a tertiary amine, we're going to name these as N-substituted primary amines. So what do I mean by that? Well, if I have, for example, put a few different groups on here, a couple different groups on here. So here we have a tertiary amine, right? All of these have the lone pairs of electrons, or I'm just not drawing them in. I don't typically draw these in unless we're about to use them, but I'm going to stick them in there, make it look a little bit more appropriate. So our tertiary and our secondary amines are going to be named as N-substituted primary amines. What do I mean by that? N-substituted means that instead of a number, we're going to use a capital italicized N to let someone know that the group you're about to talk about is hanging out on the nitrogen. It's bonded to the nitrogen. So we're going to find our longest continuous chain. In this case, I'm looking at an ethyl group or an ethane derivative any way I cut it, right? Because if I were to pick the isopropyl groups, the methyl group would be a substituent. So I'm going to pick the ethane to be the parent. That means the isopropyl groups are substituents and they're bonded to the nitrogen. So in order to tell somebody they're on the nitrogen, I'm going to say N, comma, N, try to italicize that the best I can. They're on the same nitrogen, so it's just N, comma, N. If they were on 2 different nitrogens, we would start using a prime or a double prime or whatever. It gets kind of complicated, right? But these are on the same nitrogen. So I'm going to say N, comma, N dash diisopropyl and that instead of ethane, it would be ethanamine. So it's named like a primary amine where we took the other substituents and we have identified that they are bonded to the nitrogen by putting a capital italicized N to indicate their position. So that's how we would name secondary and tertiary amines. What about, let's do like a stereoisomer kind of situation. Let's do, well, we could do a ring where the amino group is not in the ring. But you could have another substituent on the ring. What do you do now? So here's the deal with the rings. The functionality that's going to take priority in this molecule obviously is going to be the amine, right? So the amino group is therefore, since it's taking priority, our amino group is bonded to carbon 1. So if you're wondering, how do you decide what carbon is what number in a ring? You're looking for the functional group. And when you find the functional group or the piece of functionality, like the amino group here, then you're going to assign that to the lowest numbered carbon, because any of those carbons could be carbon 1, right? Technically. So we've decided that that's going to be carbon number 1. And then you have a choice. You can number clockwise or counterclockwise. What you want to do is then give your other substituents on the ring the lowest possible numbers. We only have 1 other substituent on the ring. If we had 2, we would have to decide, okay, which one comes first alphabetically, and then we'd go in that direction, right? We want to give our other substituents the lowest possible number. So that means we're going to go carbon 2, carbon 3. And then you have to tell somebody what type of stereoisomer you have here, because these are not, if you were to draw out the chair structure here, these are not pointing in the same on the same side of the ring, are they? So you got to tell somebody you have the trans isomer. And then we'll put a hyphen and we'll say the methyl group is on carbon 3. And then the parent is, instead of cyclohexane, it's cyclohexanamine. So what about molecules? We'll stick with, we're in our aliphatic category here. What about aliphatic amines that where the nitrogen is incorporated into the ring? So if we have a heterocyclic compound and it's an amine, we have a ring that contains the nitrogen. It's like part of the ring. So we have a couple of different ways, of course, to name these. Let me pull this down and give it its own little space here. With common nomenclature, we have special names for these. So this is, and honestly, there are very few things in organic chemistry that need to be memorized. These little common names are usually it and the functional groups. So when we're using common nomenclature for heterocyclic amines, unfortunately, we do have to memorize these names. This thing is called piperidine. So that's going to be common. Put a little C in parentheses there. The systematic nomenclature would be to identify that you have a 6-membered ring. So it would have been cyclohexane, right? And to indicate that the nitrogen is actually part of the ring. So see up the top here, we've got cyclohexanamine, or in other words, if this was common nomenclature, cyclohexylamine. But the amino group is on the outside. It's bonded to the ring. In the heterocycle, the nitrogen is part of the ring. So this is named a little differently. It's named after the cyclohexane, but you got to tell somebody that one of those carbon positions is occupied by a nitrogen. We have a prefix that we use for that. It's aza. So we say aza and then cyclohexane. So this will be systematic. Show you, I'm going to give you 4 examples because these are pretty common, really common actually, in the lab. We got a 5-membered ring that can contain the nitrogen. And that thing is bonded to a hydrogen. We typically just write the hydrogen sort of floating in space next to the nitrogen. You can draw a bond to that if you like. The common name for this is pyrrolidine. So that's our common name. And just like we did with the 6-membered ring, we're going to indicate that we have a 5-membered ring. So we have a cyclopentane, but we want to tell somebody that one of the carbon positions has been taken up by the nitrogen. So we're going to say we have aza cyclopentane. I'm going to erase these to get in the way. This would be good for like lecture notes, but since I'm telling you this in this video, it's not really necessary. Just to give us some space. Okay, so of course we have a 4-membered ring. All of these, remember, are aliphatic. We'll have aromatic versions of these too. So we've got azetidine. That's the common name for that four-membered ring with containing the nitrogen. Of course, aza, cyclobutane would be the systematic name. And if you had something other than a hydrogen on the nitrogen, you would indicate that you had a group. So you'd name the alkyl group, and you'd put that capital italicized N, right, to indicate that it's on the nitrogen. I could give you an example in a sec. I want to just do the three-membered ring real quick. So remember, with epoxides, we had a three-membered ring where one of the carbon positions was occupied by an oxygen. We can also have a three-membered ring where one of the positions is occupied by a nitrogen. And all of these have their lone pairs, right? So this is called an aziridine. Or aza, cyclopropane. And like I was saying, you could have like a group attached to the nitrogen. So just make something up here. Right, and I want to tell somebody that that's a vinyl group, right? I want to tell somebody that's on the nitrogen and not on one of the carbons. So I say this is N-vinyl. Azacyclopropane. Or you could also say N-vinyl aziridine. Sometimes we overlap the systematic and the common nomenclature. In all reality, these heterocyclic aliphatic amines are usually referred to by their common names. So we would call that N-vinyl aziridine. But aza is something that you should be familiar with. It is a prefix that indicates the amino group. So these are our aliphatic amines. What about our aromatic amines? So aromatic amines are going to be named after the aniline or some of them are so common that we just have common names for them. So systematically, we're going to use the common name because aniline is actually the common name, right? But this is where we're going to overlap them again, the two different systems. So systematically, we're going to use the common name aniline to name in any of the nomenclature, right? Unless it's a very specific type of heterocyclic aromatic amine. So, for example, this is aniline. We covered aniline, or at least introduced it in the aromatic chapter. So that right there is just aniline. So if I have an aromatic amine, but I have like a group attached to the ring, like say this, what I have is meta nitro aniline. And of course, if I had something other than a hydrogen up there on the amino group, I would have to say I have N dash whatever that other thing is, and then 3-nitroaniline. So just so you can specifically tell somebody where something's hanging out on that molecule. What about aromatic amines that are heterocyclic? So like say for example, I take these up here, my 6-membered ring and my 5-membered ring, and whoops, what if I incorporate that nitrogen into an aromatic system? So now, right, instead of azacyclopentane, right, or instead of pyrrolidine or piperidine, we could do the 6-membered ring as well, I have pyrrole. So instead of pyrrolidine, I have pyrrole. This is almost always referred to by its common name. We'll talk just a second. Let me get this other one drawn in for you about the aromaticity of these compounds, because when you're looking at the number of pi electrons, you might be surprised to discover that not all of the electrons are going to be part of the pi system here. So this is pyridine. Instead of piperidine, we have pyridine here. When we're doing chemistry with these particular compounds, it behooves us to understand the geometry of the electrons. Meaning, like, if your lone pair of electrons is part of the pi system, like in pyrrole, so that lone pair of electrons is actually lying in the same conjugated system, right? So geometrically, those p orbitals are, those electrons are part of a p orbital that's in line with the other p orbitals in the aromatic ring. The lone pair on pyridine, though, is not part of the pi system. So the lone pair of electrons on the nitrogen in pyridine are actually lying parallel to the ring. In other words, they're perpendicular to the conjugated pi system. When you're choosing which one of these molecules to actually use in a synthesis, that's going to be pretty important. So if you're using one of these molecules, trying to use one of these molecules as a nucleophile or a base, you want to keep in mind, like, hey, what's the electron geometry going on for those particular electrons? So in pyrrole, our lone pair is part of the pi system. It's conjugated, so part of the aromatic system. And in pyridine, you have 4n plus 2, in other words, 6 pi electrons. The lone pair is not part of it. Another couple of sort of celebrity heterocyclic aromatic amines that you might be familiar with. If you've done any work in biology with DNA, you've seen this before. So this is part of a couple of base pairs. Again, we have lone pairs of electrons. The lone pair of electrons on the top, so this right here, just like pyridine, that lone pair of electrons is not part of your pi system. So these are. And you might be wondering, what does that matter? Well, if the lone pair of electrons is conjugated, right, with, if in an unhybridized p orbital and it's lying in that conjugated pi system with the other pi electrons in the aromatic ring, they're not as available, right, to be used. So you see that lone pair and you think like, okay, I'm going to use those to grab a hydrogen off of an acidic molecule, or I'm going to use those as part of my nucleophile. They're part of the aromatic system. And the aromatic system is quite stable. If you use those electrons, you bust up aromaticity. Across the molecule, you have another nitrogen with a lone pair of electrons, and those electrons are lying perpendicular to the pi system. So their electron geometry is different, right? They are available, or they're more available to be used as a base or as a nucleophile. This particular compound is known as imidazole. And you'll see this in DNA quite frequently as part of their base pairs. Another one, so if we want to do a six-membered situation, there's never any real good way to draw these because it takes up so much space. This right here is called pyrimidine. And both lone pairs in this molecule, so both lone pairs of electrons, are not part of the conjugated pi system. So if you were to draw, and when I'm talking not conjugated with the pi system, let me draw just pyridine again for you so you can see what I'm talking about. So I've got my conjugated pi system, and I've got, let me put this in a color that can, let's do a different color. These p orbitals, not the easiest thing to draw very clearly, but I'm trying to show you that these are all sticking up above and below the ring, right? So all of these electrons in the aromatic system are in these unhybridized p orbitals, right? That are sort of sticking above and below the ring. These, though, the lone pair on the nitrogen, imagine that's coming out at you. Guess I didn't do a very good job of that. So this is coming out, lying in the same plane as the ring. So geometrically, that lone pair of electrons is lying at a 90-degree angle, sort of perpendicular to the pi system. So in terms of, I guess, physical properties, when we're talking what is special about these amines, you really need to focus on the types of reactions that these particular compounds do not typically undergo, while other molecules that seem like they would behave similarly actually do, meaning substitution and elimination reactions. So amines do not undergo substitution and elimination reactions, right? Alkyl halides, alcohols, ethers, whatever, they all have these electron withdrawing groups that are bonded to an sp3 carbon, sp3 hybridized carbon, just like amines. However, amines don't undergo the same types of reactions as those other compounds do. So the amines' lack of reactivity in those types of reactions, substitution and elimination reactions, can be better understood um, by comparing the leaving ability, right, or the ease with which the leaving group or the electron withdrawing group can take off, right? Because isn't that part of what has to happen in a substitution or an elimination reaction? Your leaving group has to leave, and it needs to leave pretty easily. With alcohols and ethers, we can protonate the oxygen and encourage the leaving group to take off by making a weaker base. Not necessarily possible, right, for amines. Why is that? So we have to talk a little bit about the physical properties of amines. And I want to compare them to those other groups. So the easiest place to start, I guess, is to just quickly list out just some stuff that we notice about these molecules. They're polar. So this will be physical properties of amines. Because I want to compare these and their reactivity to that of alkyl halides, alcohols, ethers, whatever, right? So these amines are polar compounds. Primary and secondary amines can hydrogen bond. Right, because the nitrogen is directly bonded to a hydrogen. They are basic. These are actually the most common organic bases. They are derivatives of ammonia. After all, ammonia is a weak base, right? So in other words, what do we care about that? An aqueous solution of amines would be a basic solution, in other words, right? And amines that have, say, 6 carbons or less, because they share similar intermolecular forces with water, small amines, meaning less hydrocarbon character, are water soluble. Right? If you increase the amount of hydrocarbon character, you're increasing the non-polarity, right? The non-polar nature of the molecule. So a smaller amine, so something like methylamine or ethylamine or whatever, is water soluble. Something else that we probably can remember from the aromatic chapter is that aliphatic amines are going to be more basic than aromatic amines. We can look at pKa values for that. An easy place to start would be just like what we did with phenol and cyclohexanol when we were talking about alcohols. We could compare cyclohexylamine with aniline. First of all, we remember from the aromatic chapter that the aromatic group is weakly electron withdrawing. And so if you're going to be using these molecules as a nucleophile or as a base, you want the lone pair of electrons on the nitrogen to be more available to either attack an electrophile, right? So an electrophilic piece of another molecule. So if you're using it as a nucleophile, if you're using it as a base, you want the lone pair of electrons to be more readily available to deprotonate another molecule. So to take a relatively unhindered um, acidic hydrogen off of another molecule if you're going to use it as a base. So you ask yourself, sort of like without even knowing the pKa values, like in which molecule do you think that that lone pair of electrons is going to be more localized on the nitrogen? And if you had to pick, just looking at the structures, and you see the aromatic ring directly attached to the nitrogen, and you know that the aromatic ring is a conjugated pi system such that I can delocalize electron density into the ring, plopping a negative charge on one of those carbons. By resonance, I would guess that the lone pair of electrons on aniline would not be nearly as available for use, right, to attack something else, meaning they're not nearly as localized on the nitrogen. They're more delocalized into the electron withdrawing group, right? Or they're being pulled in the direction of the aromatic ring. But you can draw this out. You can pretend that you're going to use these as a base. So just put them in water. These are weak bases, so we're using our little reversible arrows there. This will be in equilibrium, in other words, with its conjugate acid, which has a pKa, right? The pKa for this is almost 11. Down here, we're going to use aniline as a base, or we're going to try. And if we did, we'd protonate the nitrogen, right? Because you're using the lone pair of electrons to attack a hydrogen off of the water molecule. The pKa for this is just under 5. Remember, the lower the pKa, the stronger the acid. What that means for us is that this is a stronger acid and this is a weaker acid. Therefore, this has to be a stronger base. And this must be the weaker base. You could also draw resonant structures to further convince yourself. If you didn't have those values available, you could say, well, what can I do with aniline that I can't do with cyclohexylamine? I could take the lone pair of electrons on aniline and I can delocalize them. Remember, we were saying you want those electrons to be more localized on the nitrogen because you want to use them, right? It's like having liquid funds versus tied up in stocks, right? You want to use your money. We want to use these electrons. But with aniline, we can delocalize these electrons into the aromatic ring such that they're not nearly as readily available to deprotonate something else. And I can then keep going with this, right? Just like we did in the aromatic chapter. Draw your resonant structures. Essentially, and there's a positive charge here, essentially what's going on is you're showing that the electron density is sort of not super localized on the nitrogen. And you can't do this with cyclohexylamine because the electrons are not part of a conjugated pi system. There's no place, how are you going to delocalize them, you know? You don't have that conjugated pi system. So there are no resonance structures on alkylamines. So in other words, aliphatic, like cyclohexylamine. And so therefore, their lone pairs of electrons are more available for use, meaning they are stronger bases. Or better nucleophiles, right? When we're comparing, so this is just speaking about the amines, but when we're talking about the different types of reactions that amines can actually undergo, we can compare these to that of other pieces of other functional groups like alcohols, ethers, alkyl halides, whatever, which are able to undergo certain reactions. So amines can be used as nucleophiles. Amines can be used as bases. We can react them with acids, right? We can synthesize, we can reduce them, right? So we can reduce, not amines. We can reduce, say, like nitro benzene compounds to make amines. We can use amines as nucleophiles, and we'll definitely show more examples of that in the coming chapters with the carbonyl compounds. We can use them in alkylation reactions in order to prepare ammonium salts. We can alkylate ammonia in order to make amines. So there are some reactions that we can show, but these things typically don't undergo some substitution and elimination reactions. And the easiest way to sort of try and make sense out of this is to compare their pKa values, so the pKa values of their conjugate acids, to that of the pKa values of the conjugate acids of the leaving groups in the functional groups that actually do undergo these reactions. So alkyl halides, alcohols, ethers, and amines all have electron withdrawing groups bonded to an sp3 hybridized carbons, but amines do not undergo substitution and elimination reactions like the other molecules do. So we're going to take the relative reactivities, starting with the most reactive, and I'll just keep it sort of generalized. We'll draw R, CH2F, right? And then underneath this, we'll say if the leaving group is the fluoride ion, then its conjugate acid is HF, right? Makes sense. So that is going to be the electron withdrawing group attached to your rest of your molecule. Fluoride is going to be the leaving group. Its conjugate acid is hydrofluoric acid. The pKa of the conjugate acid for hydrofluoric acid is 3.2. Remember, the lower the pKa, the stronger the acid. And HF is a weak acid. And I say that because we're going to compare it to, we'll say R and then CH2. And we'll say, how about an alcohol? The leaving group for this would be hydroxide. We already know that that's a strong base, right? Because we just talked about it in the alcohol chapter. Its conjugate acid is water. Its pKa is 15.7. That's something you can actually calculate if you're ever interested, using the Ka expression and the concentration of hydronium ion and hydroxide in the autoionization of water. So if you're curious where the 15.7 comes from, you can actually figure that out yourself. But we're trying to figure out, like, hey, if I'm going to do a substitution or an elimination reaction, I care about the leaving ability of the leaving group, don't I? The stronger the base, the poorer the leaving group. The weaker the conjugate acid, the stronger the base, right? So this is why we're comparing pKa values. We have an ether. I should probably say, instead of greater than, this is kind of almost equal to, right? Kind of depends on what the R groups are. But your leaving group would be OR minus, right? You'd have an alkoxide anion, and its conjugate acid would be the alcohol. Now, again, depending on the alcohol, the pKa value is approximately 15 or 16. So it's kind of on par with water. And then we have amines. So again, highlighting the leaving group. The actual leaving group in this particular amine would be the amide anion, which is conjugate acid would be ammonia. Its conjugate acid is actually a weak base. And the pKa of ammonia is 36, meaning it has such a high pKa value, it's not even an acid, right? We know ammonia is a weak base. So if the pKa value is so high, the base, right, the conjugate base of ammonia, the amide anion, must be a pretty strong base. So this is a very strong base. This right here will end up being the least reactive in any reaction that requires NH2 minus to leave. Of these, this will be the most reactive. And when we talked about substitution elimination reactions, and we went through what are the conditions for, encouraging certain substitution or elimination reactions along, we were talking about SN1, SN2, E1, E2. The leaving ability of the leaving group was a consideration that we had to make for all of those reactions. And when we went through the awesomeness of the leaving group, we found out that of all the halogens, fluoride was actually the worst. So on this list of most to least reactive, the alkyl fluoride is the most reactive. And the fluoride anion is a crappy leaving group in the first place. So it is far better than the amide anion, right? Protonating an alcohol. So you might be wondering, like, hey, in the alcohol chapter, we talked about how you could encourage an alcohol or an ether to undergo a substitution reaction by protonating the oxygen and creating a weak base, which is a decent leaving group, right? So protonating the alcohol, for example, we take, say, just ethanol. Plus some proton. Activates the molecule toward attack, doesn't it? Because this right here is a good leaving group. Right? We have protonated the alcohol. We have turned hydroxide would have been the leaving group if we tried to do this reaction on just the alcohol. This is a poor leaving group. Because it's a stronger base. But try that with an amine, right? Because here we have the pKa of this protonated ethanol is negative 2.4. The lower the pKa, the stronger the acid. So that tells us that that water molecule is a pretty decent leaving group. The pKa of the conjugate acid of the alcohol is, you know, negative. So pretty decent acid, pretty weak base, good leaving group. On the other hand, take ethylamine. Protonate it, because you figure we're going to create a better leaving group because it'll be a weaker base. And the pKa of this is actually 11.2. So protonating the amino group does make it a better leaving group, but it's not nearly as good as a protonated alcohol. The lower the pKa, the stronger the acid. So 11.2 is not very low, right? Not a very good, not a very strong acid, meaning its conjugate base must be pretty strong. The pKa of our protonated alcohol, negative 2.4, it's a pretty decent acid, meaning its conjugate base must be pretty weak. So in other words, unlike protonated alcohols, protonated amines cannot undergo substitution elimination reactions. It doesn't mean you can't protonate an amine. You just create a quaternary ammonium salt. And you can use that in a chemical reaction, right? The lone pair on the nitrogen is going to therefore allow the amine to react both as a base and a nucleophile. So if you just left it alone as the amine, if you protonate it, we consider that an acidic molecule a weak acid that is basically a delivery system for a proton. It is not basically a good candidate for a substitution or an elimination reaction. So there is some value to protonating amines. Salting out amines, for example, is a sweet way to deliver certain alkaloid medications, which are often oils. or liquids. Salting them out to make the hydrochloride salt allows us to form pills to give people, so there, we can deliver protons in solution using an quaternary ammonium salt. We can encourage the formation of a terminal alkene by encouraging a quaternary ammonium salt to take off as a leaving group, right? Depending on what is actually bonded to the nitrogen. But something like this, just ethylamine, even protonating it doesn't make it a good leaving group for a substitution elimination reaction. So a lot of these reactions that we're going to talk about dealing with amines as nucleophiles and bases are going to come up in the chapters with carboxylic acids and carboxylic acid derivatives like esters, acid chlorides, anhydrides, that kind of stuff, and also aldehydes and ketones. But I do want to show you a few reactions that you can do. Because these are good bases, we can allow them to react with acids. So we can allow these to react with acids to form ammonium salts. So I could take, say, methylamine and aqueous HCl, so hydrochloric acid. And what I get is the ammonium salt. Which, by the way, has a name. So you would name this just like you would a regular amine. So we would have methyl, but instead of amine, we have, because we have an ammonium ion there, it's methylammonium. And then we name the anion. Just like Gen Chem with the nomenclature of ionic compounds, you name the cation first and then the anion. But with these, we have to say what alkyl groups are actually on the nitrogen, if any. I could take, I guess, just ammonia. And I could do let me move this down a little bit for you. I could do an alkylation reaction. An alkylation reaction is where you're going to add an alkyl group to something. So in this case, I'll alkylate ammonia by allowing it to react with an alkyl halide. So again, this acts as a nucleophile. It's going to do, in this particular case, an SN2 reaction, so a backside attack on the electrophilic carbon in ethyl bromide. Bromide is going to leave. So effectively what you get and then your spectator ion is up here, right? So this is an equilibrium with the amine and the acid, which is probably not fair to say is an equilibrium, right? Because HBr is a pretty strong acid. These reactions are fairly instantaneous, right? You'll just get like the salt. You let an amine get anywhere near an alkyl halide or a source of acid, instantly you just have white powder on your hands. Let's see. We could do an intramolecular one. We haven't done really anything like that yet. We could use an amine as a nucleophile, and it can do an intramolecular SN2. So something like this. Did I form a 5-membered ring? Plus HBr. Or you could say it's in equilibrium with the salt. I could, let's see, I could reduce other nitrogen containing compounds to form amines. I'll save the reduction of amides for the carbonyl chemistry because we haven't really introduced the carbonyl functionality yet, but we can reduce nitrogen containing aromatic compounds like nitrobenzene. There's a couple of different ways that you can do this. You could take, let's put an electron withdrawing group para there. We'll take hydrogen gas, we'll take a metal catalyst, a good one. Platinum is good. And I would get the aniline. Or, if I wanted to, there's another set of reaction conditions. I could say in the first step, I'm going to allow this to react under acidic conditions in the presence of some tin. In the second step, I'll just hit this with hydroxide. So there's two different types of reaction conditions there to achieve this end. So we can reduce other nitrogen containing compounds to amines if you want to synthesize them. There is one, so we say that amines don't undergo substitution and elimination reactions, but we do have one, and I'm thinking about it now, elimination reaction that we can do with an ammonium salt that will allow us to create what you might consider the less likely to form alkene according to Zaitsev's rule. So instead of the more highly substituted alkene, we could actually synthesize what you'd imagine to be the less substituted alkene. So we could do an elimination of an ammonium salt. And we need alkyl groups on this nitrogen, not just hydrogens, right? To form a terminal alkene. So when we were talking about elimination reactions in that chapter, we went through, regiochemistry, stereochemistry, all that kind of stuff. Zaitsev's rule told us that the transition state associated with the more stable alkene would be the alkene that has more substituents on the carbons, right? And so therefore we would expect if you were getting two products out of an elimination reaction, the major regioisomer would be the more heavily substituted alkene, the one where the double bond was further into the molecule, not hanging off the end, right? This reaction I want to show you allows you to actually synthesize a terminal alkene, if that's what you would like for the next step in your, whatever synthesis you're doing, by encouraging a quaternary ammonium salt to take off. This very specifically is called a Hofmann elimination. I always spell this guy's name wrong, and it's probably wrong again, but that's okay. So in the Hofmann elimination, we take a molecule where you might expect the major product to be the more heavily substituted alkene if you were to make an alkene from this thing. So if you had any other, like if this was just like a chloride or a bromide or whatever. So we take our quaternary ammonium salt and we allow this to cook up with a source of hydroxide and some water. And what you get is your less substituted alkene, trimethylamine, probably aqueous sodium chloride. We'll just account for the water that way. So what's going on here? So we've got our starting material. I'm going to draw this just to make it a little easier to see. Oh, did I put too many? Yeah, that was right. I'll leave the spectator out of it. I'm going to grab that hydrogen. These electrons are going to collapse between these two carbons, and this is going to take off. This is an E2 reaction. We'll just draw the important products that come off of that. So you end up with a terminal alkene. Where otherwise, if you were to do an E2 reaction on, say, like an alkyl halide or whatever, you would expect that your more stable alkene would be the more heavily substituted alkene, or the more highly substituted alkene, or an alkene that's sort of like more interior in the molecule. So this is a type of elimination reaction that we can do with a quaternary ammonium salt. Other reactions that we can do with alkenes, with amines, we can use amines as nucleophiles. I'm going to list this as a type and then say we're going to cover these using amines as nucleophiles. In upcoming chapters with carbonyl containing compounds. So we can allow them to react with aldehydes, ketones, carboxylic acids, acid chlorides, acid anhydrides, whatever. We can reduce amides to produce amines, all that. So we'll end up using those in upcoming chapters. With carbonyl compounds. Carbonyl compounds are special. The carbonyl functionality is hugely important in organic chemistry, and we have a host of functional groups with the carbonyl functionality, the carbon double bond oxygen functionality, and we will have separate videos just for those. So this is going to do it for amines.